Hello and welcome to our webinar, Generation of 3D Imagery by Oblique Systems. This webinar is hosted by Phase 1, GGS, and Skyline Software. My name is Oodi Menaker. I'll be your host. On your screen, there is a place for questions. If you have questions during the presentation, please write them and we will take the questions after we finish the presentation. So my name is Oodi Menaker. I'm the product manager for Phase 1 operational softwares. I also pilot the tests all the Phase 1 cameras in flight. Together with me is Gerhard Kemper. Gerhard is the founder and the CEO of GGS, and he is an engineer and photogrammetrist. And also we have here Itai Ben Schechter. He is the Director of Technology and Services of Skyline. Phase 1 develops and manufactures spatialized industrial camera systems and imaging software solutions that provide accurate megapixel size imaging. Our solutions are used for aerial mapping and surveying, ground and aerial inspection, agriculture, machine vision, cultural heritage, and homeland security. Our headquarters is in Copenhagen, and we have R&D centers in Copenhagen, Israel, and Japan, and we have sales and support offices in North America, in Denver, in Germany, and in Hong Kong. Phase 1 has a range of products that supports aerophotography, starting with the cameras themselves. We have aerial cameras from 50 megapixels to 280 megapixels, including near IR cameras that combine with the RGB give us the 4-band solution. We have a controller. The IX controller is an industrial fanless computer. It has 2 SSD drives that holds 1 tera of memory, and it has 6 power outlets and 6 USB ports. And this is actually the center of the system. We record the images on this and we do the power distribution, and operational software sits on this computer. The operational softwares are IXPlan for flight planning, IXCapture, with which we do the camera control and image acquisition and monitoring, IXFlight, that is our flight management solution with the flight director, sensor and control and triggering. And we have the IXCapture, which is used, we have the Capture One, which is used for image editing and image management. Together, all these parts with GPS and stabilizer, we make a full system, and we have a full aerial system that PAS 150, PAS 100, and PAS 280 aerial mapping systems. Those are fully integrated systems. Phase 1 has a range of products, a range of lenses that supports flight at any altitude. So the customer that buys the cameras can match them with any lens that he needs based on the flight altitude. And now to the oblique imaging. The oblique imaging, we use nadir forward and aft and side looking cameras. With the nadir, we get the usual nadir imagery. And with the forward, aft, and side looking, we get precise imaging of the facades of the buildings. And if we have vertical terrain sites, also we get very good imaging of vertical terrain. We can see locations from multiple views, and when we process all the images together, we can do extraction of RGB point cloud, reconstruction of textured 3D model, geospecific models, and the user can do visualization and analysis, 3D analysis and visualization at 3D. It is used in multiple applications that require high accurately 3D. It is used in urban planning, for example. You can do 3D scanning of a city, and then, for example, you replace a place with a high building and see the effect of this building on its environment. You can do also simulation. Emergency response can know better routes using 3D. Environmental monitoring and climate simulation is done using 3D models. And of course, cultural heritage documentation and disaster management and regular 3D GIS applications. This is an example of an image taken by GGS and generated with Skyline software. And you see here a model showing a fire-burnt area in the city of Wissembourg in France, and the user with the correct application can go around and check the damages and estimate the exact damage to the area. A major decision in Oblique system is to select the correct camera. Usually the basic aspect of selection of the camera is the typical flight height. What is the height that you're going to use the system? And based on the height, you usually select the lens. Another consideration is how much work you have there, and this will dictate which cameras you'll take, usually not for the nadir, but for the sites, whether you want to go for cameras with less megapixel that will be less expensive. You also want to consider options for multiple use, like whether you're going to do nadir mapping or not, and whether you need multi-band solutions, which means that you need another RGB camera, another near IR camera looking at the nadir. The IXM series is ideal for oblique systems because of the very small body. It's easy, you need 5, 6 cameras in there, so a small body becomes an advantage. It has very good resolution and large dynamic range. The choice of lenses make it highly flexible. So many systems select the RS150 as the nadir, and it used also for mapping, and they select the IXM 100 often for use for the oblique, because this is it gives enough resolution for oblique. The selection of camera, usually the major consideration is long focus versus short focus. So if we look at the pros and for long focus versus the pros for short focus. So with the long focus, we fly high. We have low building lean. We'll get the smooth GSD distribution into obliques, and we'll be able to get high resolution at a higher flight altitude. And when we fly high, we have less restrictions because when we fly low over cities, we have a lot of restrictions. And because long focal lengths mean lower angle, opening angle, we have less risk of vigneting in the camera hole. When we look at the short focal length, it has a wider angle and perspective views. The lenses are usually smaller, so they're compact, easier to integrate in a system with 5, 6 cameras. It gives better resolution in mapping, and because of the wider angle, you have less flight lines. It is usually smaller and lighter, so it's easier to, the system itself will be lighter. And it has, because it is small, it has more flexibility in angle setting. These are 3 examples of Oblique Systems made with the phase 1 cameras. On the left, it's ATS Berlin system that is operated by Ofek Air in Israel. In the middle, this is the OIS XL 4-band system made by GGS. And on the right, this is the IGI made Urban Mapper. All of them use phase 1 cameras. And with this, I will transfer the stage to Gerhard Kemper. Gerhard is the CEO of GGS.
Thank you, Oodi. So, okay, I think I have now the screen. Welcome everybody to the webinar this afternoon. I think Oodi already has introduced ourselves a little bit. So we are since 1980, so already 30 years on the market, and we are a system integrator, and we do a lot of integrations for multiple sensor setups, or for example, RGB 4 and 5 band, thermal, hyperspectral, LiDAR. We have our own portfolio on UAVs, our aerospectre line. And of course, we do the oblique camera systems. And we also have own product line of stabilized mounts, interfaces, GNSS, INS, and flight management. And we are specialized in integrating for the customer needs. So what you name it, we deliver. And we have opened our branch in Turkey and in France this year. So we are globally active. So coming to the next slide. Okay, that's actually the 3 models where we integrate the phase 1 cameras. It's the OISL. It takes 150 megapixel as a nadir and 4 times 100 megapixel as an oblique. Our second model is the XL 4-band system, which uses 150 megapixels in nadir as a 4-band solution, and the 4 cameras 100 megapixels in the oblique. And actually, we are designing the big version, quite a big stuff machine with a 280 megapixel camera in the nadir and 4 times the 150 megapixels in the oblique. That's definitely a mass of data that are generated during the flight. We use the technology of phase 1 with a daisy chain setup. So we integrate the flight management system, which triggers the camera. We have the cameras in a chain, and we have the GPS INS data at the backside of the daisy chain, and this one is corresponding with the flight management system. We store the data on the IX controller and display and operate them. This is an example of our body. It's open, and you see here the camera with changeable angles, and we can change all the different lenses and also the orientation of the cameras, as for example, have all cameras forward looking in the portrait or landscape format. Yeah, calibration procedures, that's something which we typically take in our consideration. So there's on one step, it's a camera calibration, radial distortion, PPS, and focal length. And this is typically done by 2 entire image blocks in 2 flight altitudes, and also flying overlap that guarantees adjustment of single cameras. So when you fly oblique, you either can use all cameras in one setup in one big block, so all 5 or 6 cameras together, or you can fly in a way that you have the possibility to calibrate each camera separately. Bore side calibration, also quite important. The mount angles must be considered, and the lever arms in the camera coordinate system has to be applied to the mount angles. And of course, the mount angles by mechanic, they are not as precise as the IMU gives the values, so a final bore side calibration is a must. And of course, the IMU measurement center to the nadir camera, that's something which is more or less traditional, but also these angles are calculated out of the AT results, for example, by Photomesh, or we do it in the next step after Photomesh with Bingo to have a fine calibration here. And the camera-to-camera calibration is also very important, especially in the oblique setups. And we sometimes have to take into account how the rotation parameters and the rotation matrix is applied, that the backward-looking camera may have to be flipped for the later processing in the softwares. And of course, we have the displacement of the 4 nodal points of the oblique cameras, and they typically have to be applied to the nadir camera as a master. That's I already mentioned, that the images may have to be rotated. That's an example of an image block where all cameras in 2 flight altitudes have been adjusted together. It's a point matching, and then we make the bundle block adjustment in Bingo. And then we go in 2 steps for the calibration. So we have the radial distortion, and after solving the parameters, you see very small remaining pixel issues in the shift parameters in the radial distortion. Well, that was a bit too fast. Oblique mission planning, there's some difference to traditional planning. You have to take all footprints and of course the terrain into account, especially the terrain of the oblique cameras have a massive influence on the footprints and the coverage. Cameras, lenses, mounting angles and orientation, and all of them together affect the number of flight lines. And typically the overlap is 80% forward and side lap of 60% to get a proper data set for the processing pipeline. Overlaps and side laps may have to be increased depending on the structure of the areas. So it means deep road canyons, for example, at skyscrapers. So this influences the design of the overlap and maybe also the setting of the viewing angles. This is an example of an area of the, I think it was the 3 centimeter flight over Speyer, where we may see from ETI later some examples. So that's actually the area we wanted to capture. And so you see more flight lines to cover the oblique views of this area. So oblique flight definitely needs more flight lines. These are the parameters, and very important is also to select by the speed the time between 2 shots to be sure that the images can be stored in related to the frame rate of the cameras. That is an overlap analysis in our software to check out if we may skip a flight line or shift the block and save some costs in flight planning. Workflow description. So the installation, it's quite similar to a normal aerial survey installations. Of course, we have a bigger camera and typically a bigger stabilizer than with a single camera. And stabilized mount is definitely recommended because especially the sideward looking cameras are very strong affected by roll effects during the flight. Monitoring the proper capturing of all cameras, that's a must. So if one camera got stuck, so the daisy chain may block all cameras and you have to refly. So always take into account that you're inside the burst rate of the cameras and you capture the images in a proper way. Especially if you fly a high resolution project, it means it's a very short base length between the single shots and you use 6 cameras. And when you have tailwind, for example, that sometimes can cause that you cannot capture as fast as it may be needed. So that's some things which are, let's say, more critical than with a single camera setup. Workflow description for the data pre-processing. So before we enter the final data processing, for example, in Skyline Photomesh. So the images are typically stored in cameras in each folder, and the images themselves are geotagged. It means they have in the EXIF information the real-time solution of the GNSS-INS, which is not very precise. It's something around 1 meter and 0.1 degree. And there is beside that an EXIF log generated in the same folder with a precise timestamp of some nanoseconds. And this one is important for the synchronization of the later post-processed GNSS-INS data to get them merged with the images of each image container from the camera. the processing of the genus data together with the mount data and the timestamp data, and also the solved lever arms, which is mainly done already by the calibration process. And the direct reference is received when we use the event file. So we use typically the EXIF log for each file container. So we have the image name and the exact time, and then we apply the floating lever arms, offsets, and of course a borside correction. That way we receive, of course, the exact position and attitude parameters for each photograph. And this one nicely can be entered then into the processing pipeline. Another quite important task, if I already mentioned, but maybe some images have to be rotated to apply the parameters of the attitude correctly and the orientation of the image correctly. And in some cases, during the processing from raw to TIFF, you have to take into account that sometimes you have headlight and you maybe have to correct in Capture One the lines in a different way than the other views. So left and right side sometimes have different light conditions.
Thank you, Gerhard.
Yeah, you're welcome.
And we now go to Itai Ben-Schechter from Skyline.
Hi, everyone. Thank you so much for joining the webinar, and thanks to Phase One and Oodi for hosting us. So a quick overview of Skyline. We specialize in 3D reconstruction, and we are also, and the whole concept of performing analytics and disseminating the data over the internet. So this is something that we've been doing for over 20 years now. And we are also added Photomesh into our suite of products for the 3D reconstruction. Photomesh is capable of handling extremely large data sets, really unlimited amount, given the proper amount of storage and the proper amount of processing power. The scalable architecture for Photomesh allows to run on multiple computers. So that's how we're able to scale up on large projects. We call it the Photomesh Fuser technology. It does not require really high-end computers. Only a basic 16 gigabytes of RAM, 8-core computers can be used as a fuser. And that's how we can also utilize cloud technology to scale up using the more affordable machines. I think the most amount of fusers we ran in parallel on the cloud was close to 500 machines, definitely plus 400. And we typically run projects that go north of 100,000 of images, sometimes even as close as 1 million images. We have different models for using the software, whether it's pay per use or number of fusers. So we have pretty flexible models to support different customers. Next. So the input into Photomesh is really any image-based camera, any frame-based camera system, and we can also process full motion video. We can incorporate point clouds, LiDAR, whether aerial or terrestrial, and we can support really a variety of GPS accuracies, whether going from really high-end camera systems all the way to drones or even handheld cameras on the ground or from a helicopter. And we support multiple bands. We can produce up to 12 bands in an ortho, and a different combination of bands in 3D meshes and colorized point clouds. The output formats that we support, we're pretty compatible with any industry standard. We have our own 3D mesh format called 3DML. We also support OSGB, the typical open standards, OBJ, DAE, Collada, as well as SLPK and 3D tiles. The point cloud is in a LAS format that has embedded attributions such as colors and other information from the mesh production, the 3D reconstruction. A true orthophoto so pixel-based rectification for true orthogonal view, so no building lean or anything like that, and a full DSM and DTM suite. Next. We will review two projects. One of them is the one from GGS that Gerhard was demonstrating on for the flight planning portions in Speyer. That one was 4,650 images, I believe, from the combination of the 150 megapixel nadir and the 100 megapixel oblique. With the 70 millimeter lens on the nadir and an 80 millimeter lens on the oblique. Usually the oblique lenses are a little longer because they have to view a little farther. That's part of the nice configuration that Phase 1 offers, different lens flexibility for different applications. So the processing time for this specific computer, we ran it on our in-house production where we have almost 100 machines. So in this case, we did not use Amazon, but we ran it on 50 parallel computers, and the whole process took 21 hours, so under a day. Just for comparison, typical processing time trying to run this on a single computer software could be close to a month. So just to give an idea of the scalability of multiple fusers. So another project we will review that was offered by OFIC Aerial Photography, which we work with on for mapping really large-scale projects. This one was 26,585 images, almost 3,000 gigapixels, and 5-centimeter target GSD, pretty large area, large urban area in Tel Aviv, 80 square kilometers. Also a combination of 150 megapixel nadir and 100 megapixel oblique, though with a 90 millimeter lens on the nadir and 110 millimeter lens on the oblique. So slightly longer lenses, slightly higher flight altitude. This one processed on about 90 computers in under 3 days, 66 total hours, and trying to process a project of this size, which is already pretty significantly sized, over 26,000 large frame images, could easily be 6 months to crunch the pixel-based demonstration. So here we go. I'll share my screen and we'll jump into the demo. So over here, I have the Speyer project that we were looking at. We are viewing this right now inside Photomesh. These icons represent the airborne GPS location of the different cameras. And we can see the projected footprint of the camera and project it onto the terrain. So we can see the oblique image as an input into the software. And then we can also project one of the nadir images. So this is all configured here. You see the 4 left, back, right, and we can figure out which images we want to review. Initially, I mean, there's airborne GPS and IMU, so the images are pretty close, but there is a need to perform a full aerial triangulation and bundle adjustment. So what we do as a first step is we calculate all the photos, and we can see here the calculated photos through the process. And then just quickly, in the other one, I'll also review the AT report and using control points. The process for splitting up the reconstruction into tiles, and then every single tile can produce its own 3D point cloud and textured mesh. So on a single tile level, you see this is the densified point cloud. So all of the 3D points that were correlated using 2 or more images, and then the textured model, which looks like this, and or the untextured model, just the surface model, and then the textured model itself, on a single tile basis. So we can see the process of correlating really thin features, really tight areas, using a good overlap and high quality images. And through the process, the tiles are produced with a little overlap. And then we're able to combine them all together so that you can see over here, there's no stitching or no visible seam lines between different tiles. The final product itself gets produced with built-in pyramids, what's called a level of detail tree, a LOD tree, so that it's very easy to zoom out, zoom in, view the entire area. Another option we have in the software is to create water bodies. So in photogrammetry, typically water doesn't get correlated. There's no features. So you could either import a water body or digitize it on top of the 3D and then clean up the water. You can see you get a nice flat water body. Just quickly to pan around and show, one of the unique features that Photomesh has is the ability to extract edges. So we extract linear features, and you can see the linear features coming into effect in creating corners, which are pretty sharp, and roof edges. And that's part of what gets utilized in the 3D reconstruction to enhance the point cloud. So this is a very high quality aesthetic 3D model thanks to Gerhard's GGS system. And you can see with the oblique images, the ability to view things from the side, as get us very high detailed outputs, and just generally a very high quality, including small cables, poles, really anything gets correlated in the 3D basis. So now we'll jump into the other project. This is the Tel Aviv project. One of the capabilities that we have is we can split the project up into AT tiles, aerial triangulation tiles. So if a project is tens of thousands or hundreds of thousands of images, it could be processed in different AT blocks, aerial triangulation bundle blocks, and then automatically merged together. This project also has a combination of control points and type points. So just to give you a quick overview, this is a sample control point, and we can see all of the rays that were measured in the point and the triangulated location of the point. This is the actual feature that was surveyed in the control. And here in the control point editor, it could be sampled inside the nadir images or the oblique images in order to georeference the data set to an accurate location. The AT report itself reports a good residual on the output, just over 1/3 of a pixel. And we can see over here the AT report for the control point accuracy. We also perform in situ calibration. So while there could be input calibrated, lab calibrated, we can perform calibration using the aerial observation and data. So this is an example of the slight differences that could happen as a result of atmospheric conditions, changes in humidity level, air pressure, which have an effect on essentially the virtual camera model in the air. So I'll also have the project open here. So once the 3D mesh is done, it could be brought into Terra Explorer. And you can see over here, I'm displaying things such as roads on top of the 3D mesh. You can also incorporate GIS data such as 3D buildings and visualize them on top of the 3D. It's also possible to do any sort of shadow analysis, what's called a shadow query, so that you could see the effect of shadows in a certain day, and also any kind of 3D measurement, which also has special snapping tools, so you can snap to corner of a building and then get really accurate 3D measurement. So this is the Terra Explorer platform, which enables all the 3D visualization. The last thing I'm going to review real quick is the True Ortho and the DSM. So we can see here the sample from Speyer and the quality of the True Ortho and the ability to not have any building lean and really have sharp edges using the edge technology. And we can see here the quality of the DSM, also very sharp edges, and these unique features over here were rectified very well. And you will not be able to see any leaning on products, as this is not a mosaic, it's 100% a true ortho. So that's it. Oodi can grab it back. We went a little bit long, try to cover everything that might be interesting.
Okay, so in summary, Oblique Systems become a common urban mapping tool with phase 1 cameras. A large set of lenses enable systems that provide high resolution at required flight altitudes. We have integrators like GGS, IGI, and ATS that are readily available to generate high quality turnkey oblique solutions. And software solutions like what you've seen here, that Photomesh by Skyline Software, are available for straightforward, mostly automated product generation. Our presentation comes to an end here. Thank you very much for your time. If you have questions, please type them. If you have any questions, please type them into the question area and we will do our best to answer them.
I see there's a question about
there is a question. Yeah,
about digitalization. I mean, we're not going to go too much into specifics. The ability, once you have a high quality 3D mesh with edges and corners, part of what I was really lightly touching on, with the snapping tool, you could snap the corners and digitize rooftops, building facades, and all of this is exportable in 3D shapes or objects. So this is something that, with a high quality camera and a high quality collection system like GGS's, you could produce proper data for digitizing. Traditionally, digitizing used to get done from stereo imagery using nadir only, but now with obliques, like Oodi was mentioning, you have much better base to height ratio, and you can also digitize on facades using the 3D model itself, which is almost like a satellite system. The more satellites you have and the wider the angle, the more accurate the measurement. So, stereo works on traditional nadir 2-image pair, but think about the fact that a 3D model, a corner of a building could have 20, 30, even 50 images pointing at it. So triangulating all of them to the same exact point is really the most accurate representation. I see some other questions. The GSD of this project. So the Speyer project was 3 centimeters and the Tel Aviv project was 5 centimeters. There's a question about fusers, how many cores were used. So the typical fuser that we use in-house production has 8 cores. If there's more cores, they'll definitely be utilized. We try to max out the computer's hardware resources, but the minimum I would say is 8 cores and 16 gigabytes of RAM. There is a question, do you offer a way to post-process the 3D mesh to improve edge sharpening and area flattening? Yes, we have built-in editing tools, and we also allow to export the individual tiles as OBJs and edit them, and then bring them back to the software to produce the pyramided full output. So the editing can be done on a specific area and improvements, as well as we have built-in editing tools for like removing cars from the road or cleaning out building facades, sort of extruding them or smoothing them out. Is this used for military defense applications? The answer is yes. It's used a lot for mission planning, command and control, simulation. There's a lot of applications for 3D in the military and defense. There's a question, can we also see DEM and DTM in Terra Explorer? The answer is yes. You could load in elevation data and regular raster imagery, ortho imagery, and display them in what we call 2.5D. 3D is full 3D mesh model and can have a view underneath things. 2.5D is a gridded DTM or DEM with the imagery on top. So I think, there's a question about how users and Photomesh licenses organized. So Photomesh is the license model is based on how many fusers you have. The basic package is Photomesh 1, which is 1 fuser. You can get a Photomesh 10, which allows you to run on 10 fusers. And we also have the software as a service option where you can buy gigapixels. So you can purchase, 10,000 gigapixels and process an unlimited amount of fusers, which is very common on the cloud, where you can either use 10 computers or 500 computers. It doesn't really matter to us. It's based on how many gigapixels, sort of like credit. You buy credit and then you go through that credit. There's a question, if you scan a large area at different times of day, how do you adjust for shadow direction of the objects on the images? So this gets addressed both ways. One is in the aerial triangulation. Usually the shadows, if it shifts, there's other objects, other features that are utilized as tie point, especially when you view them from 5 different perspectives, and those get filtered out. On the texturing side, we have the ability to blend. So we do a blending, and we can basically average out the different shadows and create a blended texture that combines the different shadows together without having a sort of patchy effect where it's dark and all of a sudden bright right next to each other. So there's a question, how the triangulation done for oblique system, direct tie points between oblique cameras or lever arm and offset angles. So the aerial triangulation gets done automatically. We do tie point extraction between the nadirs and the obliques. And we're able to connect all the nadirs to themselves, but also all the nadirs to the oblique images automatically. This is done because Photomesh utilizes a combination of traditional photogrammetric techniques in structure for motion, but also a lot of common computer vision and more modern close range photogrammetry techniques, which is more designated for images from a lot of different perspectives. There's a question, could we also extract tiles from Terra Explorer, or can this only be done in Photomesh? Well, the tile concept is a Photomesh concept. Terra Explorer imports final products. So you can't really extract tiles because Terra Explorer doesn't know what a tile is. It's a Photomesh architecture. It's a question, assuming no GCPs, do you use PPP or PPK on the project? So if you have PPP or PPK, we have options in the aerial triangulation to change the GPS weight or the factor. So if you have extremely high accuracy input GPS and no GCPs, you can set the GPS factor to be very high, and then it really respects the input GPS to maintain accuracy. If you have control points, you can lower the GPS weight or factor and then allow the bundle block to shift to the control points to achieve the best accuracy with the control points as the guideline. There's a question about Tel Aviv Mesh seems to be less accurate than the Speyer one. Consequently of GSD or manual editing. Yeah, Tel Aviv Mesh was 5 centimeter GSD and the Speyer Mesh was 3 centimeter GSD. I believe the Speyer collect was also higher overlap. So they're both automated. There wasn't any manual editing done in terms of the general quality of the meshes. So the difference between them is, you know, Tel Aviv was a massive project, and trying to do that entire project in 3 centimeters would have been, you know, twice as many images or more. So there's financial aspects to every decision on what resolution to fly. Obviously, everybody would love to collect everything in 1 centimeter, but you know, then you have to process 1 million images and fly for a week instead of a day or 2. So there's a lot of inputs and criteria for how to decide. Can we output specific point class only? No, we don't classify the point cloud. We do allow the point cloud to be, exported as a LAS and run through different classification software, third party that we can recommend, and we have partners that do this. There's a question, is Terra Explorer a hosted solution with web viewers? Yes. So there's a Terra Explorer for web, which runs on a browser, and the Skyline Globe server can host the 3D data and then stream it into the Terra Explorer web. So that's the answer is yes. How does Photomesh deal with pictures from different light conditions, having cloud blocking the sun? So there's 2 things that we do. We have an internal mechanism called CLAHE, which is contrast limited adjusted histogram equalization. So it could dynamically correct an image inside if there's a cloud shadow and brighten only the areas that are dark. And that's for aesthetic purposes. And I also mentioned we also have the blending algorithm on the texturing side that can blend different lighting conditions and create a more uniform feel for the textured output. Question, can we import water vector polygons? The answer is yes. If you have hydrography layers and shapefiles with Z values or KMLs with Z values, you can import them into Photomesh and then you don't have to digitize. And then the answer is, can Photomesh extract water vectors? Well, if you digitize it inside the software, you can export it to a shapefile, but we don't extract it automatically. And then can DSM files be edited to smooth out irregularities? So whatever edits happen on the mesh also apply to the DSM. So if you clean out the mesh with our editing tools or with an external editing tool and then import it back into the software and export a DSM, that DSM will also have those corrections or edits in there. Another question, is it possible to import shapefile with many water polygons in it? Yes, you can import a shapefile that has 100 different features. And if they each have a unique Z value, that will be imported as well. Can multiple camera platform types be merged to create a single AT block and surf it? Yes, that's the GGS is a multiple camera platform. And we create an AT block with all of them together. So the answer is yes, that's what Photomesh does. You can have dozens of different cameras on the same project. I believe the largest camera system we processed had 17 cameras, 1 nadir and 16 obliques. How simple is it to produce a DTM from DSM in Photomesh? There's a built-in DTM extraction in Photomesh that does its best to remove above ground features. If there's LiDAR, it does work better with multiple returns. And the extension, yeah, like a Citymapper, we process Ultramap Osprey, but Phase 1 is one of our closest partners. And the IGI system, the GGS systems, all the systems we work with the new phase ones, the CMOS, are really high quality geometry and radiometry. So I mean, that's definitely some of the best outputs we've gotten. How critical is the quality of the aerial triangulation? How many pixel accuracy is still allowed for a good instrument model? So the aerial triangulation is the most critical part of the quality of the mesh. We usually achieve sub-pixel accuracy correlation between all of the cameras. The two projects I showed were around 1/3 of a pixel. It could get down to 1/4 of a pixel. If it's above 3/4 of a pixel, if you're getting an average residual of 1 pixel or more, the mesh might not be very crisp or very clean. There's things in the software you can do to generalize it or smooth it, but it's not going to be as accurate of a 3D product. So I would say 1/2 pixel or better, which is usually achieved through automation in the Photomesh aerial triangulation suite. The use of LiDAR helps in the mesh generation? Yes. If it does it have to use trajectory data or last file? We don't need trajectory data. We can use just a standard point cloud, a last point cloud. What we do is we compute the trajectory by comparing the LiDAR points clouds with the image-based point cloud, and we create our own trajectory for the LiDAR points to be able to establish the normals, the normal vectors for the surface creation. So the question, can LiDAR data be used to assist in computing type points? So no, the LiDAR is used to enhance the point cloud, which is the base for the surface creation, the mesh creation, and the texturing later on. But it's not really used to assist in computing type points. The LiDAR can be used to extract control points. So you can use the LiDAR intensity to sample features in the LiDAR, like markings on the road, which I showed was a survey point, that could be a LiDAR point. So you could improve the accuracy of the images by extracting control from the LiDAR, but it doesn't automatically assist in computing type points. It's up to you, Oodi, how long you want to go. I think we answered most of the questions.
Yeah, we did answer most of the question. There is a last question, we'll answer it, and I will have to close it.
Okay, so can manual type points be added?
Question.
Yeah, that's the last one. Yes, manual type points can be added if there's issues with overlap or an area that didn't correlate perfectly. You could load a connection map and see if the connections are good. If not, you can manually add a type point and improve that area for the bundle block adjustment. The answer is yes.
Okay, thank you very much all for your participation. You will get within a few days a mail with a link to the recording of the session so you can review the slides, questions and answers again. Thank you all very much.
Thank you.
Bye-bye.
Bye.
Bye.